Hello everyone, I'm Shweta. Currently, I'm a research scientist at Huawei Technology India Private Limited. Prior to that, I have completed my postdoc from Technion Israel, and before that, I have completed my PhD from IIT Hyderabad, India. My research interests are progress guarantee in software transactional memory systems, parallel and concurrent programming, distributed systems, and blockchain. Today, I, along with the co-author Archit Samani, are presenting our work titled A Novel and Efficient Way to Achieve Starvation Freedom in Multi-Version Software Transactional Memory Systems. We are really happy to present our work at SNIA SDC India 2021, and we're really thankful for them for this wonderful opportunity. The agenda of today's talk is, I'll start with the introduction to STMs. STM stands for Software Transactional Memory Systems. And then I'll cover the related work on starvation-free read-write STMs. And after that, I'll give the motivation towards starvation-free multi-version RW STMs. And that causes several challenges that I'm going to discuss in this section. After that, I'll describe the proposed algorithm, which is starvation-free K-version RW-STMs. And then I'll show the efficacy of our proposed algorithm with the state-of-the-art STMs in performance analysis. And I'll conclude my slides followed by future work. So let's talk about introduction to the STMs. So before going to the STMs, let's try to know about what is memory transactions. So memory transaction is a sequence of instructions executing in the memory, and that should satisfy the atomicity property. Now, what is software transaction memory systems? So it's a parallel programming paradigm that avoids the concurrency overhead at programmer level and execute the code optimistically. So basically, STM is a library that gives the interface to the user to execute their sequential program to concurrently and efficiently. Traditional STMs invokes STM begin, STM read, STM write, and STM try commit methods. So STM begin allocates the unique timestamp to each transaction. STM read the T object from the shared memory, and STM write updates the T objects into the local memory. Whereas the STM try commits validate the consistency or validate the updates made by the particular transaction. And if all the changes made by the particular transactions is consistent, then the particular transaction returns commit and the changes made permanent into the shared memory. Otherwise, the respective transaction returns abort. So let's understand the execution of STM better through this example. So for this, we have considered an algorithm which wants to insert the element E into the linked list LL. So it's been invoked by a thread to insert the element E into the linked list LL. So this method has been executed through the transactions. So it executes sequence of instructions in such a way that the line number 2 is getting the unique timestamp through the STM begin, and after that, the linked list is the thread is identifying the appropriate location to insert the element E into the linked list using the STM read function. And then STM through the STM write, the thread is updating the element E with the value V prime into the local memory. And at line number 8, it's validating the changes made by the transaction. So if it's returning successful, then it's well and good. The thread will come out from the loop and it will execute it successfully. If not, let's say if some other conflicting transaction is executing on the same location, then what will happen? This transaction will return unsuccessful. Then it will retry from the line number 2 again. So if such scenario will again occur again and again, then what will happen? The particular transaction will abort again and again, and the particular transaction will starve. So the issue may arise here is starvation. So such situation should not occur. So in order to get rid of the situation, we are proposing the starvation-free K version read-write software transactional memory system in this talk. So a well-known progress guarantee associated with the concurrent programming is starvation-freedom. An STM system is said to be starvation-free if a thread invoking a non-parasitic transaction TI gets opportunity to retry TI on every abort due to the presence of fair scheduler, then TI will eventually commit. So here, non-parasitic transaction means that if the transaction TI is getting the request to commit, then it will try to commit the transaction. But the another progress guarantee is wait freedom, which says that every transaction commits regardless of the nature of concurrent transaction and the underlying scheduler. But it was shown in the literature that it is not possible to achieve the wait freedom in dynamic STMs, in which datasets of the transactions are not known in advance. So, in this talk, we are going to explore the starvation freedom for transactional memory systems while assuming that the dataset of the transactions are not known in advance. So, in order to do that, let's understand the related work on the starvation-free STM first. So, starvation freedom in STM has been explored by a couple of researchers in literature. In the case of conflict between two transactions, the transaction with the lowest priority is being aborted. And it maintains the single version corresponding to each T object. So that's why we are calling it as a SFSV-RW STM. So here SV stands for single version RW STM. And basically these STMs work on the read-write primitive. So that's why we are calling it as a read-write STMs. They ensure that every aborted transaction on being retried a sufficient number of time will eventually have the highest priority and hence will commit. So it would be clear with the example. Here we have considered an example in which there are three transactions, transaction T1, T2 and T3. The transaction T1 invokes the read operation. R stands for read and W stands for write operation, and subscript represents the operation of the particular transaction. So here one represents the read operation, R1 represents the read operation of transaction T1 on X T object. So it's returning the 0 value. Similarly, the read on Y T object returning the 0 value. And at the same time, like concurrently, the another transaction T2 and T3 wants to write on X, Y and Z data item. So what will happen here? We are assuming that the lowest transaction is having the highest priority. So the transaction T1 is having the highest priority, and the other conflicting transaction T2 and T3 are having the lower priority than T1. So that's why on conflict, the transaction T2 and T3 both are returning abort, whereas the transaction T1 is returning commit. C1 stands for commit here. So we think like, can we reduce the number of aborts? So that's why we explored the multi-version software transactional memory systems. And this example gives us the motivation towards our proposed algorithm, which is starvation-free multi-version RWSTMs. So now let's talk about the motivation towards starvation-free multi-version RWSTMs. So this is the same example that I have already explained. Now I'm going to explain like how this example is gonna be provide the greater concurrency while maintaining the multiple version corresponding to each T object. So here there are again the same example, 3 transactions, but here instead of maintaining the single version corresponding to each T object X, Y and Z, here we are maintaining the multiple versions. So if the conflicting transaction with the highest priority is reading the conflicting data item, whereas the another transaction can also create the another version and commit concurrently. So in this setting, while maintaining the multiple version, all the transactions T1, T2 and T3 all returns commit with the equivalent serial schedule T1 followed by T2 and T3. So the takeaways for this talk is like starvation-free multi-version RWSTMs reduces the number of aborts and increases the throughput. But it poses several challenges. So now I'm going to explain the couple of challenges here. the challenges for the starvation-free K version RWSTMs. We are calling it as a SFK-RWSTM. So, although the starvation-free multi-version RWSTMs provide greater concurrency, they suffer from the cost of garbage collection. For the solution is like, as we are knowing, like multiple version maintaining the multiple version is taking a lot of space, so we need to do the garbage collection. But the garbage collection is also interrupting the normal methods of the RWSTMs. So the solution for it is starvation-free bounded multi-version RWSTMs, where the number of versions is bounded to be at most k. Thus, when k plus 1th version is created, the oldest version is going to be removed and replaced. So achieving starvation freedom while using only bounded version is especially challenging, given that a transaction may rely on the oldest version that has been already removed. So, in order to address those challenges, like we have proposed the starvation-free K version RWSTMs. So this is our proposed algorithm. So let's talk about the proposed algorithm. So we developed our SFK RWSTM algorithm in a stepwise manner that starting from the MVTO protocol. So MVTO is a well-known protocol in the literature, which stands for multi-version timestamp ordering protocol. So we start with this, and in a stepwise manner, we reach till the our proposed algorithm SFK RWSTMs. So initially, we proposed the PKTO algorithm, which is priority-based K version timestamp ordering algorithm. That was not satisfying the starvation freedom, but it was correct. So that this was not serving our purpose. So we proposed the next algorithm, which is starvation-free K version timestamp ordering algorithm. That was ensuring the starvation freedom, but it was not correct. So eventually, we proposed our algorithm, which is starvation-free K version RWSTMs. That is ensuring the starvation freedom as well as it's correct. So it's serving our purpose. So in this algorithm, we are maintaining like each transaction maintains 3 timestamps. First one is current timestamp. So this is a unique timestamp allocated to the transaction Ti when it begins. And the another one is initial timestamp. This is same as the CTS when a transaction Ti starts for the first time. And the third timestamp is working timestamp, which stands for WTS. This is a unique timestamp for transaction Ti. So this is derived, WTS is derived from the CTS and ITS with the formula is CTS plus C multiplied by CTS minus ITS, where C is any constant greater than 0. When Ti aborts and restarts later, it gets a new WTS, but it retains its original WTS as ITS to help ensuring the starvation freedom. Along with this, each transaction maintains a timestamp range, transaction lower timestamp limit, which is TLTL, and transaction upper timestamp limit, which is TUTL. And these timestamp ranges are helping to ensure the real-time order. And here the timestamps are monotonically increasing, and version created by a transaction Ti for a T object X is denoted as Xi. And as we know, it's a bounded version. So in this algorithm, we maintain K version corresponding to each T object. The data structure of the SFK RWSTM is its list of list. So we are maintaining all the T objects in the form of list, and each T object maintains a version list again in the form of list. So each version consists of 3 fields: timestamp, value, and read list. So here we have considered k is equal to 3. So there are 3 versions. For the sake of simplicity, we have represented with the timestamp 5, 15, and 25, with the value v5, v15, and v25 respectively. So here read list represents the what are those transactions who has read from this particular version T5. So here the transaction T6, 9, and 12 has read from this particular version, and so on. So this is the basic data structure we have maintained it for the SFK-RW STMs. Now let's understand the efficacy of our proposed algorithm through the performance analysis. So in order to do that, we have done our experiments on 2-socket Intel Xeon CPU, which has 14 cores per socket and 2 hyperthread per core. So a total of 56 logical thread it has. And the machine has 32 GB RAM and run on the Ubuntu 16.04.2 LTS. So here we have considered the T object as 5 and the operations per transaction as 10. And we have considered 3 workloads. First is read intensive workload, in which we have considered 90% read and 10% write. Another is mid intensive workload, where we consider 50% read and 50% write. And third is write intensive workload, in which we have considered 10% read and 90% write. So this picture is showing the comparison of our proposed SFK-RW STM algorithm with state-of-the-art STMs. So here there are 3 figures A, B and C, and each one is of for the lookup intensive, mid intensive and the update intensive workload. So here the x-axis shows the number of threads, whereas y-axis represents the maximum time taken by the transaction to commit in milliseconds. So lower is better. And for this, for the state of the art, we have considered PKTO, SFSV, RWSTM, ESTM, and the NORIC STM. Those are the popular STMs in the literature. So here we can see that for each of the figures, our proposed algorithm is performing better than state of the art STMs. And our proposed SFK-RW STMs gives an average speed up on the max time to commit of a transaction by a factor of 1.22, 1.89, 23.26 and 13.12 times over PKTO, SFSV, RWSTM, NORIC and ESTM respectively for the counter application. So we have also shown the efficacy of our algorithm through the state-of-the-art STMs on the STEM benchmark. So basically, we have considered 2 applications from the STEM benchmark. One is K-mean and another one is labyrinth. So here again, the same thing is x-axis represents the number of threads and y-axis represents the max time taken by a transaction to commit in milliseconds. So here also lower is better. But here the K-mean is a low contention workload. So here we have analyzed that our algorithm is not best among state-of-the-art STM. Here, state-of-the-art STM NORIC is performing better than our algorithm. Whereas for the labyrinth algorithm, which is high contention workload application, so here our algorithm is performing best. So we can conclude that our algorithm is performing best on the high contention workload. So SFK-RW-STM performs 1.5 and 1.44 times better than PKTO and SFTM, but 1.09 times worse than NORIC for low contention K-mean application of the STEM benchmark, whereas it's performing better with all the state-of-the-art STM on labyrinth, which is high contention workload. It's time to conclude the talk, followed by the future directions. So here, I have given the motivation towards the starvation-free multi-version STMs, and we propose the starvation-free K-version RW STMs, which ensures free starvation freedom while maintaining the K version corresponding to each T objects. So it also ensures the correctness criteria as well as the starvation freedom. And our experiment shows that SFK-RW STM performs better than starvation-free state-of-the-art STMs as well as non-starvation-free STMs under long-running transactions with high contention workload. And one of the interesting future direction could be achieving the starvation freedom for the nested STM, where one transaction internally invoke the another transactions. It could be the interesting avenue. Thank you so much for listening our talk. The full version of this talk can be identified in this link. For any queries, feel free to reach us on these email IDs. Please take a moment to rate this session. Your feedback is important to us and we'll be available during the session to take your questions. Thanks once again.